Hello everyone. In this session, we'll discuss about serial communication in 8086 processor. Now, before going to discuss something about serial communication in 8086, let us see what is a communication. So, communication here is nothing but transfer of information between two entities. Okay. So, if there is any exchange of data between two entities, two endpoints, or two systems or two machines, will be considered as communication. Okay, now this communication is classified into two types. Okay, that is parallel and a serial. Now what is parallel communication? So as the name itself saying that simultaneous or more than one. Okay, so here if here multiple bits are transmitted at the same time. Okay, so if multiple bits are transmitted at the same time, then that kind of communication will be considered as a parallel communication. And then what is serial communication? So here a single bit is transferred at a time, at a single time or at any time, so it is called as a serial communication. So or else we can also call it as a bit by bit data transfer happens in case of serial communication. Okay, let us see how these circuits look like. Now here this is a serial communication and this is a parallel communication. As you can see, in case of serial communication there is only one channel. Now this channel can carry one bit of information at any time. Okay, so as there is only one channel, so only one bit is transferred at any time. Now after transferring that bit, after transmitting or receiving that particular bit, now the next bit will be transferred. Okay, but when it comes to parallel communication, as you can see here, multiple channels are present. So here each and every channel is capable of carrying one particular bit. Okay, therefore as we have in this particular example, as this is having totally 8 data lines, so it can carry up to 8 bits at any time. So that is why it is called as a parallel communication. So multiple bits are transferred at the same time here, but whereas here a single bit is transferred. Okay, now here when it comes to the advantages of serial communication, here as this particular implementation is very simple, and the cost for implementing this particular communication is very much less. But when it comes to parallel communication, here the speed of transfer would be very much high as compared to this serial communication. Now when it comes to the drawbacks of this serial communication, here the speed of transfer is very much less. It takes much time for transferring the data. But when it comes to parallel communication, here there would be a choice of noise to degrade the message. Okay, so that is the main drawback which is present in this parallel communication. And here this system looks very complex, so whenever any system is complex, then the cost which is required for implementing the system would be very much high. Okay, so this is what serial and parallel communication. Now let us see the transmission types. That is, there are some transmission types in case of serial communication. Those are simplex, half duplex and full duplex. Now what is this simplex? So simplex is also called as unidirectional communication. As you can see here, there is one unidirectional channel which is present in between the transmitter and the receiver. Okay, so the data is always transmitted from the transmitter to the receiver, but whereas the receiver cannot transmit the data back to the transmitter. Okay, so that is why it is called as a unidirectional communication, or else a simplex communication or simplex transmission. Okay, and the best example for this is radio communication. Okay, and the next one is half duplex communication. As you can see, there is a bidirectional channel, but only one single channel would be providing the two directions. So that is why at a time only one particular action takes place, either transmission or else receiving. If one device is acting as transmitter, then the other device should act as a receiver. So simultaneous transmission is not possible in case of half duplex communication. Okay, and the best example for this kind of communication is in walkie-talkies. Okay, and the last one is full duplex communication. As you can see here, there are two independent channels. One is for transmission and the other is for receiving purpose. So as these two channels are independent, therefore simultaneous transmission occurs in case of this full duplex communication. Okay, and the best example for this is telephones, mobile phones. So all these communications or all these applications would be using this full duplex transmission. Okay, now let us see the transmission modes in case of serial communication. There are basically two transmission modes in serial communication. they are synchronous and asynchronous. Now what is this synchronous? So in case of synchronous, the transmitter and receiver are synchronized with the same clock, or a common clock is given to the transmitter and the receiver. Okay, so as there is a common clock, so both the transmitter and receiver would operate with the same speed. Okay, now but when it comes to asynchronous communication, here two independent clocks are given, but the clock's value must be same. It means if I'm applying a 2 kilohertz at the transmitter, the same 2 kilohertz should be applied at the receiver. Then only the communication takes, or successful communication takes place. Okay, so here synchronous, which is having a common clock, and in case of asynchronous, two independent clocks, but the value must be same. Okay, now let us see synchronous transmission, how it is going to be implemented. As you can see here, there is one device, there are two devices. Basically there are two devices. Okay, in case of asynchronous, we call the first device, or the device which transmits the data will be called as transmitter, and the device which receiving the data will be called as a receiver. Okay, but when it comes to synchronous communication, here one of the device would be considered as a master, and the other device would be considered as a slave. Now why it is called as a master? Because master is responsible for generating the clock, as well as for initiation, as well as for termination of the communication. So if any device is generating the clock and initiates and terminates the communication, now that will be considered as a master. Okay, and the slave will always receive this clock signal. Okay, so if any device is receiving the clock signal, now that device would be considered as a slave. Okay, as you can see here, there is one master which is generating the clock, and there is one slave which is receiving the clock. Okay, now here we have two variants here. As you can see, there are two independent channels for data here, and there is one clock channel. But when it comes to this type, here we have only one clock and then one clock channel, and then we have a bidirectional data channel. Okay, as just now we have seen, it looks similar like full duplex communication, and it is identical to half duplex communication. Okay, now here, so as I told you that master will be generating the clock, and that will be transmitted, and now that would be received by the slave. So slave would be operating with the clock of the master. So as a common clock is shared between the master and the slave, so both would operate with the same speed. Okay, so if any changes in the master, the same changes would reflect at the receiver side. Okay, so the communication takes place without any noise or without any error. Now let us see asynchronous communication. Now in case of asynchronous communication, we have to use independent clocks. Okay, independent clocks. Now what happens in asynchronous communication? How the data will be transmitted? Okay, so if we have a message, or else if you have a character to be transmitted, now that character would be undergoing one process that is called as framing. Now what happens in framing? In framing, every character is appended with some bits. Okay, now those bits are start bits, stop bits, and there is one optional bit that is a parity bit. So here the original character is added with 3 more bits, start, stop, and a parity bit. Okay, and the resultant frame will be considered, and the resultant message would be considered as a frame. Okay, so framing is nothing but adding these 3 bits to the message bits, and the output of that framing process is a frame. Okay, now as you can see here, initially assuming that the transmitter on the right side and the receiver on the left side, as you can see here, initially start bit is transmitted, and then the original message, and then a parity bit, as I told you that it is a optional one, and then the stop bit. Okay, now here start bit indicates start of a character. Start bit tells the receiver that it is the start of a character, and here stop bit indicates the receiver that it is the end of the particular frame or a character. Okay, now as you can see, stop bit, here it is a start bit, and a start bit is represented with a logic low, and stop bit is represented with a logic high. Technically speaking, start bit is called as a space signal, and the stop bit is called as a mark signal. Okay, here we are showing how character A is transmitted. Now character A ASCII value is 41, as we know that every character, every special symbol, every numerics will be represented with the help of ASCII format. And the number of bits required for representing a character or else an alphanumeric character by using ASCII is 8 bits. Okay, so here these are those 8 bits, start bit and a stop bit. So this is how now this complete information would be called as a frame. Right, let us see what is this Usart and a transceiver. So Usart, the name indicates, or the name stands for Universal Synchronous Asynchronous Receiver Transmitter. Okay, so it can provide synchronous communication as well as it can also provide asynchronous communication. As we have seen what is synchronous and what is asynchronous communication. Now it would be acting as an interface circuitry between the microprocessor and the serial port. As we know that microprocessor will not have any kind of ports. So in order to communicate with the external serial peripherals, then the processor needs to have some ports. Now those ports are given with the help of this Usart. Okay, so it would be acting as an interface between the microprocessor and the serial port. Okay, now this Usart can also be called as a serial to parallel or else a parallel to serial converter. Why? Because the processor will support parallel data, but whereas the external peripherals, that is serial peripherals, would understand only serial data. So if processor is transmitting the parallel data, if it is directly given to the serial peripheral devices, then they won't understand. So we need to convert that parallel into serial form, and then that serial information should be given to the peripherals. Okay, now in the same way, if serial peripherals are transmitting the serial data, now the processor is going to understand the parallel data. Therefore, there again we need one serial to parallel converter. So parallel to serial and serial to parallel conversion will be done by this Usart. Now this Usart will operate with TTL voltages, which is nothing but logic 0 is represented with 0 and logic 1 is represented with a 5 volts or else a maximum VCC. Okay, but if you want to use this for long distance communication, then we cannot directly use these TTL voltages. Why? Because as we know that as the voltage which is used for representing the data is very less, therefore there might be a chance of a noise to be introduced in the message signal. So that is why we'll use a kind of protocol to avoid this noise in the message signal, that is RS-232 protocol. Okay, now here as you can see, Usart voltage ratings, that is 0 volts, that is binary 0 is represented by 0 volts in Usart, but whereas RS-232 is going to represent the same binary 0 with a voltage in between 3 to 25 volts. Okay, and binary 1 is represented with 5 volts by Usart, and RS-232 is going to represent the same binary 1 in between the voltage minus 3 volts to minus 25 volts. Okay, now these TTL voltages are also called as positive logic voltages, and these RS-232 voltages are called as negative logic voltages. Why? Because here the logic 1 in case of Usart is represented with a positive voltage, but whereas in case of RS-232 it is represented with the negative voltages. Now let us see what is that Usart which we are going to use for interfacing or to act as a mediator between the processor and the serial peripherals. Okay, and that IC name is 8251. Okay, so 8251 is the IC whose name is Usart, Universal Synchronous Asynchronous Receiver Transmitter. Okay, now it can act as parallel to serial as well as serial to parallel converter. Okay, now here it is provided in 28 pin DIP package. Let us see the pin structure of 8251. As you can see, there are totally 28 pins, 14 on the left and remaining 14 on the right side. So there are totally 28 pins are present for this particular pin structure. Okay, or for this particular IC. Now each and every pin would be having its own important functionality. Okay, let us see those things. Before that, let us see the block diagram of 8251 Usart. As you can see, this is the block diagram of 8251, where data bus buffer is having an 8-bit data bus. Now this data bus would be interfacing or would be connected to the system bus of the processor. Okay, and here we have a read-write control logic. As you can see, some input pins are present for this read-write control logic, where it internally has some registers, as well as this control logic would be providing some control signals. Okay, and whenever we are interfacing on the modem, then we have to use this modem control signals. Okay, and apart from these things, as you can see, one internal bus which is connected to all these peripherals or all these blocks, and then we have a parallel to serial converter while transmission, and then serial to parallel converter while receiving. Okay, and we have a transmit control block and a receive control block, which are going to control the operation of these buffers, that is transmit buffer and a receive buffer. Okay, let us see them in detail. So as we have seen, it has a data bus buffer, read write control logic, modem control logic, and then transmitter section and a receiver section. So initially we'll start our discussion with data bus buffer. Okay, so here it contains a 8-bit data bus. Now this bus is going to carry information of 3 forms. One is data, status, and the other one is control information, or else a command word. Okay, now we have a read write control logic. Now it internally contains 3 registers. Along with 3 registers, it has 6 input signals. Okay, now the main functionality of this control logic is to provide the control signals to different blocks of 8251. Now let us see the importance of each and every pin. Okay, so here the first pin is CS bar. Now this CS bar is an active low pin. Now it is used by the 8086 microprocessor for selecting a particular chip. Okay, so whenever the processor wants to communicate with any kind of chip, then it is going to send a logic 0 through this particular pin. Okay, and then we have C by D bar, as you can see here. So C indicates control and D indicates data. As we have seen that data bus can carry data information as well as the control information. Okay, now this particular pin is going to intimate the 8251 whether regarding the status or regarding the information present on the data bus. Okay, now if this data bus is carrying data information, then this particular pin would become 0. Okay, it indicates 8251 that the information present on the data bus would be a data. Okay, and that should be stored inside the data register. Okay, and if this particular pin is 1, okay, then it indicates 8251 that data bus is now carrying the control information, and that should be stored inside the control registers. Okay, and WR bar, which is nothing but write bar. Now this is again an active low pin, and this pin is again used by 8086 processor to intimate 8251 that it wants to write the data to the 8251. Okay, and RD bar, which is nothing but read bar. Now it is again an active low pin. This is again used by the processor to intimate the 8251 that it wants to read the data from the 8251. Okay, and then we have a reset. It is an active high pin. So if a logic 1 is given to this particular pin, then 8251 will be reset and it enters into idle mode. Okay, and then we have a clock input. As we know that every peripheral requires a clock signal. Now that clock signal will be given with the help of this particular pin. Now let us see the registers which are present inside the control logic block. Now the first register that we come across here is control register. It is a 16-bit register and it is divided into 2 parts. One is mode word register and the other one is command word register. Okay, now here mode word register would be specifying the parity bits, stop bits, all those things are specified with the help of this mode word, and command word is used for controlling the operation of 8251. Okay, and then we have a status register which indicates the current position or current status of 8251, and it is an 8-bit register. And we have one more register, that is data register, which is going to hold the data. Okay, and it would be acting as input as well as the output port when C by D pin is low. Okay, now as you can see the pins here, that is CS, C by D bar, WR, read, and then operation. Now with the help of these pins we'll come to know what kind of operation that the processor is presently performing. Okay, so as we know that CS bar should be 0, then only the chip would be selected, and here C by D bar is 0, so it means data is present on the data lines, and WR is 1, so it means it is disabled, and RD is 0, it means that Now the processor wants to read the data from the data register. Okay, MPU reads data from data buffer. Okay, and again CS bar is 0, C by D bar is 0, which again indicates data. Now this time it wants to write the data which is present on the data bus onto the data register or data buffer. Okay, and then we have C by D bar again with 1, which indicates that now the data bus is carrying control information, and here WR is 0. It means that control information should be written into the control register. Okay, in the same way for the read operation. Now if this CS bar is 1, it means the chip is not selected, therefore irrespective of these signals, okay, so it doesn't happen anything with the 8251. Okay, now let us see the command register. As I have told you that it is an 8-bit register where every bit is having its own functionality or the importance. Okay, so here EH is nothing but enable hunt. Now this particular bit is programmed. If you are programming this particular bit to logic 1, it means it would be searching for a synchronized character. Okay, and then we have IR, which is nothing but internal reset. Now if this particular bit is programmed to 1, then 8251 would be in a reset state. Okay, so instead of giving a logic 1 to the reset, we can also program this particular bit to logic 1 to make 8251 to enter into the reset state. And then we have RTS, which is nothing but request to send. So if you program this particular bit to logic 1, then RTS pin, there is one pin which would be holding a logic 0. Okay, and then we have ER, which is nothing but error reset. Now if this is programmed to 1, then all the error flags inside 8251 will be initialized with zeros, or else will be cleared. And then we have send break character. If this particular bit is programmed to 1, then it will send a break character. So whenever this particular bit is programmed to 1, then the TXD pin of 8251 would be holding a logic 0 for a period of 1 character, which is going to differentiate the frames. And then we have RXE and TXEN, which are used for enabling or disabling the transmitter as well as the receiver sections. Okay, and then we have a DTR, okay, data terminal ready. Now if this particular bit is programmed to 1, then this particular pin would be holding a logic 0. Okay, now let us see mode instruction register, now, or else mode word register. Now it is different in asynchronous communication as well as in a synchronous communication. Okay, now let us see the importance of this register in case of asynchronous communication. So here we have S2 and S1 bits. These two bits are used for selecting a particular or else the length of a stop bit. Okay, so as you can see here, if you are going with a combination of 0 1, so it means we are going with 1 stop bit. If it is 1 1, it means we are going with two stop bits. 1 0, then it means we are going with 1.5 stop bits. Okay, and then these two bits are related to the parity. This is for enabling the parity, and this is for selecting the parity, which is nothing but either we can go with even parity or else we can go with odd parity. Okay, and L2 and L1, these two are the bits which are used for selecting the length of a character. So we can represent a character with the help of 5 bits, 6 bits, 7 bits, or else 8 bits. But in most of the cases we'll be using 8 bits, as we know that every character in the general scenario or else the real-time world would be represented only with the 8 bits. Okay, that is ASCII representation. And then we have last two bits, B2 and B1, which are used for selecting a particular baud rate. Okay, you can go with 1x speed, 16x speed, or else with 64x speed. Then we have the same mode register in case of synchronous mode. Okay, so here SCS, which is used for selecting the number of synchronous characters. So before communication takes place or starts in synchronous communication, it would be sending synchronous characters. Okay, now those synchronous characters are used for synchronizing the transmitter with the receiver. So here we can send one synchronous character, or else we can also go with 2 synchronous characters. Okay, and then we have ESD, which is for internal synchronization or for external synchronization. And then again we have parity bits, that is we can enable the parity, and we can go with either with odd parity or else with even parity. And we have 2 more bits, that is L2 and L1, which are used for selecting the character length, as we have seen in case of asynchronous mode. Okay, and these 2 bits are not used in case of synchronous communication. then we have a status register. As I told you that it would be representing the current state of the 8251. Okay, so here DSR which would be representing the status of DSR pin. Okay, it would be representing the status of DSR pin. So it would become 1 when DSR is 0. Okay, and then break data, transmitter empty, RX RDY, TX RDY. Okay, now we'll discuss about these things when we come across the pin explanation. Okay, and then we have here, apart from those things, we have a frame error, overrun error, and a parity error. Now these are the 3 error flags. Okay, which is checked by the 8251 while receiving the data. Okay, that is frame error. So if any modification in the number of stop bits, then this particular bit would become 1, indicating a frame error. Okay, so any modification in the stop bit would be considered as a frame error. That means if the transmitter is transmitting with 1 stop bit, but if the receiver has received 2 stop bits or 1.5 stop bits, then it indicates a frame error. Okay, and then we have overrun error. Now assuming that a character is present inside the buffer of 8251, now before reading that character, if the external peripheral sends one more character, then this particular bit would become 1, indicating a overrun error or overwrite error. Okay, and then we have a parity error. So if transmitter is transmitting with even parity and if the receiver has received the odd parity bits, then this particular bit would become 1, indicating a parity error in the received message. Now let us discuss about the modem control signals. There are totally 4 modem control signals: DSR bar, DTR bar, CTS bar, and then a RTS bar. All these are active low signals. Okay, now this DSR is nothing but data set ready. Whenever the modem is ready to communicate with 8251, then it sends a logic 0 through this particular pin. In response, the 8251 would be sending a logic 0 through this particular pin. Okay, and then RTS, which will be used by 8251 to request the modem for sending some data. Okay, and in response, the modem is going to send CTS signal that is clear to send. Now let us see the transmitter section. What is actually present inside the transmitter section? There is one buffer register, there is one output register, and then a transmit control block. Okay, so here whenever we want to transmit a character, now that character must be placed inside this transmit buffer. Now that is shifted into the output register. Now this output register would be shifting bit by bit data with the help of this TXD pin. Okay, let us see what is the functionality of these pins: TXD, TXRDY, TXMT, and then a TXC bar. Okay, so here TXD pin, which is used for transmitting the serial data. Okay, that is bit by bit data is transferred or transmitted with the help of this particular pin. And then TXC is the pin where we have to give the clock signal, and TXRDY, this pin would become 1, indicating the status of the buffer register. Okay, as you can see, there is one output buffer register. Whenever this buffer becomes empty, then immediately this TXRDY will hold a logic 1. Okay, and TXE is for representing the status of the output register. We can also call it as shift register. So it represents the status of output register or as the shift register. So as soon as the output register becomes empty, then this particular pin would be holding a logic 1. So indicates the processor that it has to provide one more character, or else it is ready to transmit one more character to the external world. And then we have a receiver section. So inside the receiver section, again we have receiver buffer, input register, and then a receive control block. Okay, so the data which is transmitted by the external peripheral would be received through this particular RxD pin. Now that is placed inside this input register, that is in bit by bit manner. Now after getting 8 bits of data, now that is shifted into the receive buffer register. Okay, now here RxRDY, now this particular pin would become high whenever a character is present inside this buffer register. Okay, so if any character is received by Usart, then it intimates the processor with the help of this particular pin. And then RxD, as I told you that it is used for receiving the data in a serial manner. And then we have RxC bar, which is used for giving the clock signal to the Usart. So as we have seen RS-232 protocol, Now here stands for recommended standards, and it was designed by EIA, and it is going to provide two specifications, that is a voltage and then a signals. Okay, so here as just now we have seen how logic 1 and logic 0 are represented in RS-232. So they are called as negative logic voltages. Why? Because logic 1 is represented with a negative voltage and logic 0 is represented with a positive voltage. Okay, and let us see what are those signals which are specified by this RS-232 protocol. So as you can see here, complete of 9 signals are given by this RS-232 protocol. Now out of these 9 pins or 9 signals, in case of serial communication we are using only 3 signals. Okay, those signals are transmit data, receive data, and then a signal ground. Okay, so here transmit data is used for, or this pin is used for transmitting the data, and RxD is used for receiving the data. Okay, now this is max232, which would be acting as a level converter. For example, if I'm interfacing a controller with a processor or else with a CPU, now the controller has to communicate with the CPU serial port. Now what happens here is the voltage ratings supported by the CPU serial port would be plus or minus 12 volts, but the voltage ratings which is supported by the controller would be a TTL voltages. Okay, so the level conversion should be done in between the processor or else in between the CPU and the controller, and that level conversion would be done by this max232 circuit. As you can see here, 8051 is given the output signals of the 8051 are given as input signals to the max232, and then the output of this would be given to the serial port of the processor or of the CPU. Okay, so max232 is also called as a level converter or else a voltage converter, which converts positive logic signals into the negative logic and negative logic signals to the positive logic. Thank you.